So there are, originally we were going to do this chi-square thing, which I have there kind of as a way to give you a sense of how tricky it is sometimes to interpret what does your data actually mean. And so instead of doing it, I'm just going to talk to you very briefly about what we would have talked about. Like the basic idea, like if I have coins, like here's a bunch of coins. If I flip a coin, it's a 50-50 chance it's going to be a head or a tail. That's the probability of a head or a tail if it's a fair coin. In the best case, that's what's going to happen. If I took 6 coins, or if I took 100 coins and I flipped 100 coins, due to the probability, it would say like I would predict 50 heads and 50 tails. But am I going to actually probably get exactly 50 heads and 50 tails? No. Maybe I'll get 46 heads and 54 tails or something. Does that mean that my theory about the coin being a 50-50 chance head or tail is wrong? No, it just means I'd expect it's a probability. There's randomness. However, if I flipped 100 coins and they were 100 heads and 0 tails, I would say, I really doubt these are fair coins. I think it's probably something wrong with my assumption that these coins are 50-50 heads or tails. So the reality is in real life, you have some theory, some prediction about what you expect to find. You actually look and it's not exactly what you find. And you have to say, how likely is the difference between what you predicted due to just the randomness? It's never going to be exactly what you predict. Or how likely is the difference because my theory is wrong? I predicted 50 heads and tails and I got 100 heads and 0 tails, and I'm pretty sure that means my theory that these are fair coins is wrong, or hypothesis, I should say. So this chi-squared test is basically a test that gives you the probability is how likely is your the difference between what you thought you'd find and what you did find. How likely is that just due to the randomness that you'd always find? And how much is it likely due to like your hypothesis is wrong? And the take-home message that I like to do after this whole thing is you never know for sure that your hypothesis was wrong or right, or that it was just due to randomness or not. All you know is likeliness. And again, like I mentioned earlier in lab when we were still together, I'll mention again, in the past, the convention has been, if we have an 80% greater, or not 80, 95% probability or greater that our results are real and not due to randomness, then we'll trust them. If there is a less than 95% chance that that's true, that there's a greater than 5% chance here that the randomness has kind of got under the way and we're just seeing randomness rather than some real effect, then we are officially not supposed to say that our results are statistically significant. What that means is that you have 2 kinds of errors that you can get. You can get type 1, type 2 errors. One type error is you claim that something is true when it's not true, or that the data supports it. I say like, this is statistically significant. I'm pretty sure the data supports my hypothesis, but due to our convention, there's a 1 out of 20 chance that actually it's not true, that you just got fooled by randomness. On the other side, saying you have 95% and it supports, there's still that 1 out of 20 chance that it's wrong. So it's like I'm saying, I can say, what am I saying? No, the other way. So I can say like, oh, the data does not reach this 95% confidence, so the data does not support my hypothesis. But again, you might be getting fooled by the randomness. Maybe your hypothesis is true, but the randomness got you and made your data look like it's not. So either way, you have errors where you say, I think it's real when it's not, or sometimes you say, I don't think it's real when it is. Because the randomness, you never really know for real. And when you're interpreting data, it's always about probability. And again, in the past, we've used this 95% confidence as a standard convention to say whether or not we can publish and tell other people that it seems like it's real. But that's why in your research projects, I don't want you to ever say prove. My iPad is gone now, so I don't have my iPad anymore. So I'm just gonna like write it out on a piece of paper. Don't say prove. The research doesn't prove things. Instead, research maybe will support your hypothesis or support a certain point of view, but it doesn't prove, because science never gives you absolute truth. It gives you likelihood. A lot of times, very high likelihood. It's very, very likely if we don't do social distancing right now, things are going to get way worse. It's very likely if we don't pay attention to carbon dioxide and global, these greenhouse gases, we're screwed, and actually very likely, even if we do our best at this point, we are, so it doesn't mean you shouldn't trust things, but it just means remembering that you have to keep it in the context that you have to do the statistical work to look at what are the probabilities here, because you typically don't get an absolute answer. You get, things that are, a little sample out of something that you're never going to look at the whole picture. So you have to do statistics to calculate how likely is my observation here actually extrapolatable to the biggest, to everything. So anyway, that's all I'm going to say. It's not going to be on your lab practical. It's not going to be something you got to write up. So don't worry about chi-squared. I'm going to delete the module from your are people come I'm assuming people are coming in and out, because I keep seeing things coming. I keep hearing this thing as people come in and out of my little Brady Bunch screen, but I'm not actually seeing who's coming in and out. It's kind of interesting. All right, so what we're going to do now is the lab that is exploring the respiratory system. So I'm going to share the screen from our Canvas webpage now. So it's going to take me just a second to do that. Here we go. Open that. Let me now share screen. All right. And again, chi-squared. Oh, look at this. Chi-squared. Delete. Are you sure you want to delete this module? Yes, I am. Oh, you dag nabbit. Hold on 1 second. I am logging back in. Is my screen visible to you guys right now?
Yeah.
Yes.
Okay. So let's get back into modules. Let me show you. Okay, I'm going to delete the chi-squared lab again. delete, just so you don't even think you got to do it. All right, exploring the respiratory system, doing the lab. So the first part you're not going to do in real life. I'm going to show you this little video. We're going to watch it together. It's going to be of Tina actually doing a lot of the things you would have done. So let's sit and watch Tina doing this here. And I can actually, before we go into that, I will. Oh, stagnant. Oh, let me. See, I wanted to actually. I want to share the. Oh, can you see the Exploring the Respiratory System page here now?
Yeah.
Okay, so this is what you're actually. This is from your lab manual. Just kind of showing what the steps are. Basically, you're going to be sucking air in from the room, and then you breathe out and you look at how does the air you're breathing out compare in temperature? How does it compare in water content? And then this other piece that we're doing is using lime water. And lime water is let's see, right here, is calcium hydroxide, which combines with carbon dioxide to become calcium carbonate, which is basically chalk. So calcium carbonate will actually dissolve in water and it becomes a solution. It's clear. Chalk does not dissolve in water. Chalk looks chalky. So this is going to be an assay for carbon dioxide. If we take calcium hydroxide and combine it with an adequate amount of carbon dioxide, we're going to end up with chalk. So that is important for making sense of what's going to happen here. You know, and we can actually, like if we have our lime water, the calcium hydroxide here, you can actually have this kind of, if you want to like have the room, this is like the room, so to speak, let the room bubble in here, you just have to suck through this shorter straw, and then it's going to create a low pressure zone inside the flask. And so the air from the room comes in, bubbles through. You can see what does it do in this reaction. The other option is you blow out through the long tube and bubble your own breath through the lime water and see how that affects things. So we will see as this happens in just a moment here. Okay, so let me close that. Oh, and let me get rid of all that annotation crap there. Okay, so now what we're going to do is watch Tina.
So next here we're going to do the Exploring the Respiratory System. This is part 1, composition of exhaled air. So we're going to compare the air that's here in the room, both temperature-wise and moisture-wise, and something else. And so we're going to start off looking at temperature. So right now the thermometer is showing room temperature. Next, I am going to stick this in my mouth, but not touch any parts of my mouth, and I clean it. And I'm going to exhale or breathe out a few times, and we're going to see what happens to temperature. All right? All right, so if you zoom in there, you can see that the temperature has gone up. It looks like maybe 23, indicating that the air that I'm breathing out is, of course, warmer than the air that I was breathing in. So for the next part, we're going to take a look at what kind of water content we have in exhaled air. And so for this part, I'm going to use this piece of glass. And so you can see that right now there is no water vapor or condensation on this piece of glass as it's here in the room. So next, I'm going to blow on it, and we're going to see what happens. And so as you can tell, there is condensation occurring because my breath is both warmer and contains moisture. And so it hits the cold glass, and we see the water vapor condense out. The third part of this experiment, we are going to investigate something else that's in my breath that I'm breathing out. And so for this, we're going to use lime water, which is in this bottle here. And so you can see it's semi-clear, it's pretty clear. And I'm going to pour about 150 ml. At least I need enough for this longer glass straw to be able to be fully immersed into the solution. And so then I put the stopper on, make sure I get a good seal, and check that this longer glass straw is down into the lime water. Then next, what we're going to do is I am going to put this straw, because this is where I'm going to put my mouth or lips on, and I am going to suck in air into my lungs, and that will force air to flow from the room into the longer straw. So we're going to get room air into the lime water, and then you know, we're making sure that I'm not breathing in any of the, or sucking in any other fluid, because that straw is much shorter. All right, and so after that, we're going to switch the straw over here, and then the second part, I'm going to blow my breath into the lime water, and we're going to see what happens. All right, so let's start with getting room air into the lime water. So I'm just sucking on this. And as you can see, there's nothing really happening. The lime water is still clear. So next, I am going to switch to the other straw here. And for this part, I'm going to blow my breath into the water, and let's see what happens. Here you can clearly see that the lime water has turned cloudy, and it's now up to you to read in your manual. There's a chemical reaction formula there, and then combine that with thinking about what is it in my breath that I'm breathing out as part of that chemical formula that can cause this lime water to get cloudy, or in other words, obviously we're forming a precipitate, more cloudy particle that is making this a little bit cloudy.
Okie dokie.
So next, here we're going to do the...
All right, so that, let me stop sharing just for a moment. So that is that first part. You know, in your write-up, you know, you should write what the observations are from watching this video. And then the other thing you want to do is also kind of write the implications. One of the, you know, you might wonder, you know, why do we do something as stupid as like blowing, like, you know, a sheet of glass to watch it fog up? And you're like, well, you know, it's like, that's so silly. But it's actually pretty deep when you think about what does it mean. Like, everybody has this experience. Oh yeah, you can fog up glass by, you know, putting your breath on it. But what does that really mean about your breath, the exhale compared to the air you're breathing in, right? If I take a piece of glass and just put it in the air around us, it doesn't start fogging up automatically under normal conditions, but your exhaled air does fog up. So what does that tell us about your breath compared to normal air? Somebody?
It's moist.
It's got higher water content than the air that you breathed in. So this is actually really a critical data point for when we start talking about water balance. So what is happening with every breath you take in terms of your water balance?
You're losing water when you exhale?
Exactly. Every breath you exhale, you're losing water from your body. It's part of the negative balance of your overall water balance. When we talk more formally about water balance, we'll talk about insensible water loss. This idea that no matter how much your body is trying to conserve water, there's this, about 1 liter per day that you lose no matter how much you desperately want to keep water in your body because of dehydrating conditions. So part of that insensible water loss, part of that losing water to the environment, no matter what, is coming just from breathing. Just the fact that you lose water every breath is going to be part of that, insensible water loss. So, when you're writing things up, I think making sure, like I said, at some level, it seems kind of silly. It's like, no duh, you breathe on a piece of glass, it fogs it up. But the deeper part of that is it's making you think about your water balance and losing water with every breath, and that's going to be an important thing when we look at the big picture. Same thing with temperature. Every breath you're losing heat. The breath you're breathing out was warmer than the air you breathed in, which means you had to use some of your body's energy to heat that air up. So that's part of the negative energy balance. You're losing energy to the environment just by heating up the air and then just blowing it out into the room. There's lots of other ways you're heating up the room as well, but that's one of them. And then carbon dioxide, it's not shocking, but the carbon dioxide buildup in your lungs creates a much higher carbon dioxide concentration. So when you breathe out, it's always going to be much higher than the air inside the room. So the next part. So in the pons, in the medulla, you have your respiratory control centers. These are going to be controlling kind of your breathing, whether you need to breathe, the depth of your breathing, whether or not you feel like you got to breathe. And it's a little bit non-intuitive. What is the main thing your body monitors to decide whether or not you have to breathe or not?
Oxygen level?
Right, so you'd think oxygen levels, that's what you would imagine, and it's in general not true. So non-intuitively, it mainly monitors CO2 level. The reason you feel you need to breathe is actually not because oxygen is running low. It's because CO2 is rising. So, feel need to breathe basically when your CO2 levels are going up. We can talk a little more about this later, but this is going to be important for understanding the next part of the lab. This idea that feeling the need to breathe, it doesn't matter whether there's oxygen or not oxygen. It matters how much CO2 is currently in your body. And when it hits some critical level, I really got to take a breath. If we think about, in your lungs, that carbon dioxide building up in your lungs as you're breathing, when you're doing a normal inhale, outhale, quiet breathing is only about a half a liter in and out. And again, there's about 150 mils of dead space here. So your mix, only like 350 mils of that is actually fresh air mixing with the stale air that gets down into here. It's fine for regular breathing, but carbon dioxide stays at pretty high levels down here. If I want to really lower carbon dioxide in my body, I can just what we call hyperventilate. Hyper meaning excessive. I can, like, instead of this, let's breathe really deeply and rapidly. And what's going to happen there is this carbon dioxide is getting blown out, and before it builds up, you're getting even more fresh air mixing and even more out. So the more we hyperventilate, we end up with way less CO2 down in the lungs.
Are we getting a lot more CO2 with all the masks we're wearing?
If it's affecting your ventilation, I mean, if you're not being able to breathe in as much, in general, no. But it depends. If the flow, it comes down to that thing I was showing you. If you have less oxygen coming in on a normal inhale because it's just harder to breathe in, then it would affect. It would be basically the idea of hypoventilating. Hypoventilating is the opposite. If you are hypoventilating, meaning you're bringing in less than a normal quiet breath, because it's just harder to suck air in through your mask, then you are going to be increasing the overall amount of carbon dioxide in there. But typically you're going to feel that, like you're going to, those respiratory centers in your brainstem are going to say, like, you need to breathe deeper, or, work a little harder here because the carbon dioxide is building up too high. So that's what I would say. So hyperventilating. How is hyperventilating going to affect your ability to hold your breath? If I like 20, and then I try to hold my breath, how's that going to affect my ability to hold my breath?
Lessen it?
Why?
I'm guessing there's more CO2 in your lungs and less oxygen.
So let's go back. Hyperventilating, breathing really deeply and rapidly. And
That would be the opposite.
would be the opposite. So you're bringing lots of fresh air in and you're exchanging it very quickly. So there is even more fresh air compared to dead space that's mixing, and you're exchanging it very quickly and not letting the new carbon dioxide have a chance to build up. So hyperventilating is going to really lower the CO2. It's too much of a pain to actually go back to that little model on my iPad right now. But if you increase pulmonary ventilation by having more rapid breathing and deeper breaths, your CO2 in your lungs goes way down. So if the CO2 is really low in your lungs, or in your body for that matter, what is that going to do to your ability to hold your breath?
Could hold it longer.
And why is that?
Body wouldn't signal that you have too high of CO2.
It's going to take much longer for the CO2 levels to finally reach up to that level now where it triggers like, oh, I got to breathe. So if you hyperventilate, you're going to start with very low CO2 levels. It's going to give you a lot more time to get up to that point where you actually feel like you got to breathe. Does that make sense? You know, so in the lab, let me share my screen. Back to doing the respiratory lab. And I had this thing. I put each of the pages in here as their own little page. Oh, why don't I see it? Let's just share it. Share that. So here I've got the page from the lab manual here. You can zoom in a little bit. And basically there's different conditions. One is just, this is kind of like a baseline. Take some deep breaths, time how long you can hold your breath till you just can't hold it anymore. That's kind of your baseline. This is that hyperventilation. Do 20 really deep breaths. Again, deep and rapidly. You will get dizzy. You're actually going to go into alkalosis. We'll talk more about this. Basically, as you blow out more CO2, you're going to be becoming more alkaline. It actually constricts cerebral blood vessels, and you get kind of like a head rush. You know, sit down when you're doing this. I don't want anybody like kind of face planting when they're doing their lab today. But then you might feel like an initial, like, oh, I feel a little weird, but ride it out, ride the dizziness, and then keep holding your breath and see how long you can go. And you'll probably be shocked at how long you can hold your breath after you've done a nice hyperventilation. This next one, here is your rebreathing into the same bag. In general, you know, people say don't like play with plastic bags. This is not a toy. You know, I don't want anybody like dying because they're doing this lab and they're getting like putting the bag over their head and suffocating or something. This is not about that. This is about, you know, plastic bag and really good seal. You know, so you're just rebreathing the same air again and again. So as the carbon dioxide is building up, you're rebreathing that. So this is going to be increasing carbon dioxide in your body. This does not work if you cheat and let air come in from the side of your mouth or something. That's then is fresh air. You're not rebreathing the same air. How is that going to affect your ability to hold your breath, do you think? What's your somebody's hypothesis there?
You can hold it less because there's more CO2.
Right. So if you're starting with really high levels of CO2 already, that means you're going to hit that critical point where you feel you got to breathe much quicker. So, you know, check that out. This last part, run around the building rapidly. So you know, obviously, when you do this at home, you can just do some jumping jacks, do something. You really, it can't just be like, oh, I'm moving, now let's check. It's gotta like, it's, you know, you really, or if you're sprinting in place, it's not just like, you gotta really, really go hard and really kind of get your muscles into anaerobic respiration. You gotta get to where you're going into glycolysis and creatine phosphate. So what's happening in your muscles if you start really working out really, really like hard like that.
Oxygen debt.
Totally, oxygen debt. So after you're done, you're sitting there, after you've done that, your cells are going crazy, metabolizing in order to recover from that. So you're generating lots of CO2 in your body, and it's rising up really fast, even though you're not actually doing anything anymore, right? So you're gonna see how does that affect your ability to hold your breath? Even though you're done with the exercise, you're probably going to find it's going to pretty profoundly affect your ability to hold your breath, just because those metabolic processes to recover are going to be increasing your CO2 level like crazy. So for this lab, I would like you to do, instead of having a picture or a video of people, after we're done with all this talking, I would like you to actually do this at home. It doesn't take that long. You just need a timer. You just need to breathe. Plastic bag. You know, again, don't put it over your head. Put it like in front of your face, and don't pass out and then die or something, right? So, you know, I always feel a little funny telling people to put plastic bags over their face. But again, do it responsibly. Or maybe do it if I don't know. We do have data for larger amounts of people that you can then use like for your write-up. So, but I would like you to experience it yourself, write down the results for your own personal experience with timing. And then we'll have also the data that you have that in your write-up talk about in general, what were the results that we saw when we looked across the larger group of subjects, and then put it into context. Talk about why these results make sense, particularly what I was just mentioning about how your respiratory centers decide whether you got to breathe or not. So for part 2, that's what you should be doing. You should be checking it out yourself and then looking at the group data and just putting it into context. And then the last part of this is going to be this determining vital capacity using a dry spirometer. So let me go share. So this one here, the basic idea is we're measuring lung volumes. Vital capacity is the total amount of exchangeable air. It's how much the total amount you can breathe in to the total amount you can breathe out. We're going to be looking at that in way more detail in the lab on Wednesday, but for today, we're going to do an initial assessment of it using this little dry spirometer. And let me have Tina explain it to you right now. So let's do that. I need to stop. Hold on a sec. I need to close that. Whoop. I need to get back to screen sharing. Give me a second here. That was screen share.
So now we're going to measure various lung volumes, and we need this equipment. This is known as a spirometer. This type of spirometer can only measure your exhalation. So in other words, you can't breathe in and measure any volumes. You have to blow out through it. Another limitation of this type of spirometer is that you can't just blow gently through it. It won't pick that up. So it's going to be pretty forceful exhalations that it's going to pick up the measurements on. So before we start, there are a few things you need to do. Of course, you don't want to stick your mouth on this because lots of people are using this equipment. So we have these disposable paper tubes that you would put on, a fresh one that only you have touched. And the other thing is that you need to calibrate this. And so right now it's showing some previous person's reading, and the 0 is here. And so the way you set it is that you twist. So the arrow is lining up with the 0 like that. And so now you're ready to use this and blow in here. The other thing I want to point out that some of these will report cc. So 1 cc is the same as 1 ml. So basically all these numbers are also in milliliters. Well, before we start, I want to explain some of these lung volumes. So what you have here is a graph of a person breathing in. So if the line is moving up, it means that you're breathing in. And if the line is moving down, you're breathing out. So it'll be in, out, in, out, in, out. And so what this is representing is a person just sitting around breathing quietly. So probably what you're doing right now while watching this video. And so the volume that you are bringing in and out of your lungs when you're breathing quietly is known as the tidal volume. Sometimes you see people use V and then a subscript T or TV. Either one means tidal volume. So because our instrument can only measure you breathing out and can only measure them when you're breathing more forcefully, we are not able to get the tidal volume from this spirometer. So we're going to have to calculate it. And so what we can get are some other more forceful exhalations. And so just to continue showing on this graph first, what we're showing here is someone is taking a deep breath in, as big as possible, and then they are blowing with all their might, as much air out as they possibly can. And so that is what you would be doing in this part here, figuring out your vital capacity, because this part is your vital capacity. It's the volume that when you take a maximum inhalation and you're blowing as much as you possibly can out. All right. So then we come up here and there's some more tidal volume. So I'm going to demonstrate a vital capacity using one of these spirometers. And so I made sure I have zeroed out my dial here. And then the next thing I also need to think about is getting a good seal around the mouthpiece. And I need to pinch my nose, or if you have a nose clip, that could be a good thing too. But I'm going to pinch my nose at the same time. The other thing, when you're doing vital capacities and when you're doing these volumes, you should be standing up. When you're sitting down, some of you have bad posture or slouching, you're not going to be able to measure your full lung volumes. And so because we're trying to take a deep breath in, as big as possible, it's good to stand up. And then I'm going to empty as much out of my lungs as I possibly can. And so it'd be helpful to do a little crunch or bend over to really squeeze as much air out. All right, so I'm going to demonstrate this. So all right, I had 4,100 cc in that blow. So you would just do this 3 times, calculate the average, and then you would do the other volumes as described in your lab mind.
Okay, let's see, we gotta close this. Okay, so that is the dry spirometer. In reality, there are other ways. There are different kinds of spirometers. There's wet spirometers that actually float a bell over water. And then there's more fancy kinds of spirometry that we're going to use on, pretend to use on Wednesday, which would be more accurately called a pneumotachometer. But we'll look at other ways to measure breath volumes later. But for right now, when you're looking at the data, like here, let's open up the data here. Back into doing the lab spirometry. Oh, no, it's not this one. Doing the lab, respiratory lab here. So if we look at the COVID data here, let's open this. Okay, I'm gonna have to fix this thing because obviously there's some problems with it. Or you didn't even see that, but I just had a problem with it. Let me share it. All right, so if we look at the vital capacity data for everybody, you know, the things that we ended up having the people record. Let's zoom even more. You know, we have them, their sex, their activity, like how active are they? Do they smoke? What is their height? And what was the vital capacity that they actually measured? Things like that. And then we can actually look at correlations. And so in your write-up, what you are going to want to do by a law of vision, well, I will clean this up and before, you know, in the next, in a little bit. Graphs. So let's zoom in here. This one is probably the most important graph. This graph here is something we always see. This is looking at vital capacity versus height. And what, does there seem to be a correlation here?
Yes, the taller you are, the higher your vital capacity.
Yeah, totally. And so the basic idea here is, you know, if you're taller, just you've got bigger lungs, right? It's like if you are just a larger overall human, you probably have bigger hands. And actually, you got a whole bunch more cells, meaning you're going to need more oxygen to supply them all. So a big thing about vital capacity is it's correlated to just how large you are. And in general, over doing this lab for many years, I find that that's the main thing it's correlated much more than anything else. If we, you know, there is a graph that this data, this is data, this is not from, I did not create this spreadsheet here. This looks compelling, like activity from low to high, looking like there's a big, I don't trust this actually. I'm gonna leave it in here so you can write about it if you want, but I have never seen anything like this in, you know, as I've continued doing this lab. Usually activity isn't nearly as correlated as like body size. But you can leave it in there and see. This is also non-intuitive. Usually I do find people with asthma have a smaller vital capacity, you know, partly because they have a harder time just getting all the air out of their lungs. But, you know, this is the data. You know, this smoking thing here, this, you know, this, again, having a vital capacity, an average of 2, that seems so small. But it's stuff you can play with in your write-up. Breath holding. You know, this is the data you should probably, you will use in your write-up, and you will find is hopefully similar to kind of what you find for your own personal experience. There's going to be some normal amount you can hold your breath. After hyperventilation, you know, depending on who you are, like I can typically, if I hyperventilate, I can hold my breath like a couple of minutes. It's actually possible sometimes to hold your breath so long that you're running out of oxygen even before your body feels you need to breathe, and you start, it can be a little dangerous. Rebreathing in the bag and exercise, obviously you're going to get really low times for holding because of the really quick buildup to that critical level of CO2. So for your write-up for part 2, explain why this data makes sense, and then also, see how your personal experience compares to the group results. So I will repair this data sheet, figure out what's wrong with it, and get it uploaded as soon as we're done with class today. So that is the respiratory lab. Part 1, you should be able to talk a little bit about what Tina's demonstrated with exhaled air versus inhaled air, and then a little bit about what are the implications of that? What does it mean in terms of overall physiology? For part 2, it's what we just talked about, the breath holding and how it is affected by these different things that affect the CO2 buildup in your body. Part 3, looking at how vital capacity, that basically lung size, is affected, or I should say total exchangeable air in your lung is affected by different things. Although some of the things in the data that we're going to supply to you is a little, I don't totally trust. So any questions about this lab?